All right, this is Mr. Gillum, and today we're going to learn more about squares and rhombi, but we're going to do some proofs today, and we're going to use some of the theorems that we've been studying over the last few days. Okay? Some of the proofs you're going to find are not too complicated. Let's see here. Where's my little blocker? Do a little blocker here so you can't look at all of it and just write down mindlessly what I'm writing down. Okay, there we go. Now, what we have here is we have some given information, what we're trying to prove. Okay, and I want to make sure to make this a point when we're proving it's a rhombus. So we know some things about rhombi, like if two consecutive sides are congruent, then it's a rhombus, or if the diagonals are perpendicular, then it's a rhombus, or if the angles of every vertex are being bisected, then it's a rhombus. So we know these things. So that's what I'm trying to prove, one of those things. And then once I have proved one of those things, then I know for sure it's a rhombus. So I guess when you're writing your proof, have in mind what you're trying to get to. Okay, so those are the three options. Okay, one of those things has to happen. Start out with the given information, of course, and what I did on my diagram is I just labeled everything that I know about JKLM being a parallelogram. I know that their opposite sides are congruent. I know that the diagonals are being bisected. I know those are congruent. I know opposite angles are congruent. Okay, and so I just labeled my diagram so I had a sense of what I'm dealing with here. Okay, the second piece of information, that triangle JKL is isosceles, tells me that there's a triangle here that has the same two sides that are exactly the same. So that's going to be important here in just a second. All right, so I'm going to highlight that actually. I know that this triangle is given that it is isosceles. All right, so that's going to be an important little tidbit of information. So now you got the given. Let's take a look here. It says KL is congruent to JK, and that's a big deal because if these are congruent, instead of having one dash here and two dashes here, I can put two dashes on both of them. Now these are congruent. Okay. The reason I know this is because, after all, it is an isosceles triangle. Okay. It's an isosceles triangle. So I know that KL and JK must be congruent because it has to have two congruent sides. All right. I know it's a rhombus. Boom. That took no time at all. So our options were show that two consecutive sides were the same, show that our diagonals are perpendicular, or show that our vertex angles are bisected. Now, those were our three choices this time. I cut right to the chase and I got to, well, if I know that these are parallelogram and there's consecutive congruent side lengths, then I know for sure it must be a rhombus. Okay? And so this is that theorem that we talked about. And there's some abbreviations. So if consecutive sides of a parallelogram are congruent, comma, then parallelogram is a rhombus. So you can abbreviate somehow using shapes and things like that. Just as long as you appropriate abbreviations, this should be fine. Okay, so quick one, not so bad, but I just want to keep in mind we only had to find if it was a rhombus. So we only had three different choices of what to do. Unfortunately, with squares, there's a little more to prove, and so I got the second problem here. It's got a few more steps. So this little fella takes a little bit longer to prove. In this case, we're trying to prove that it is a square, and this is where our really long proofs are going to come in. Unfortunately, it's like a combo proof, because to prove that it's a square, ideally what we will prove is that, first of all, it is a rectangle, and second of all, it is a rhombus. So to prove that it's a rectangle, the most popular way to do that, I would say, was to show that the diagonals are congruent. Okay, the diagonals are congruent. So that's the approach I'm going to take first. I'm going to try to show that these diagonals are congruent. I'm going to look at this given information. I'm just going to mark it on the diagram so I don't forget. It says SQ is the perpendicular bisector. That's important, the word bisector, of PR. So it tells me that if I'm bisecting PR, that both sides are congruent. And it also tells me that I have a right angle here. PR is the perpendicular bisector, meaning that each side is congruent, of SQ. Now it doesn't say anything about them being congruent to each other, so I can't right now mark my diagram that each of these little segments is congruent yet. That's not allowed. I haven't proved that yet. It also says that triangle RMS is isosceles. That's going to come into play here in a little bit. Okay, RMS is isosceles. Ooh, interesting. We just used that little deal here in the last one. Okay, so let's take a look here. Since I know QS is perpendicular to PR, I know that MP is congruent to MR right here. Okay, we already marked that. And I also know MS is congruent to MQ. All right, or QM. It looks like I put QM, so same thing. That's just the definition of perpendicular bisector. I just need to make sure that that's clear in the proof that all these markings, what they mean. It's part of the given really, but we also need to say, okay, well, when it says perpendicular bisector, this is what it means. That's its definition, and we already marked it. Okay. We also know MS is congruent to MR. Okay. We know that because it said this is a isosceles triangle. So I know that these sides are actually congruent. So what that tells me is I'm actually going to put 2 dashes here because now I have 3 out of my 4 little half diagonals that are congruent now. I know that MR is congruent to MS, and MS I already knew was congruent to MQ. And of course we're going to have to write all that formally in a proof. As so, MS is congruent to MP. Boom, boom, boom. I know that because I use substitution. If you look up here, I knew that MS is congruent to MR, but I knew if I plug in this MS for this MR, then I have MP is congruent to MS. So it was just a simple substitution. So now I do know that every little itsy bitsy part is congruent. I've shown that through substitution. Okay, so now if I remember, I'll go ahead and, so now we know this. We know these are all congruent. Coming on to this next page here. Oop, no peeking. All right. So we know MS is congruent to MP. Now it says MS equals MP equals QM equals MR. Now I started that with the definition of congruence because as you can see I'm using equal signs instead of congruent signs now. But also I use the transitive property. Okay, so I have this big cluster of equals, parts that are equal to one another. All right, the MS, the MP, all coming out of this. So boom, 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 boom. All right, the transitive property says that they are all equal. Now let's take a look at the segment addition postulate. And what that says is that if I add SM with MQ, it's going to equal the whole segment. If I add PM with MR, that will be the whole PR. Okay, that's just a segment addition postulate, and that's going to be important here because I need to use substitution to try to prove what I'm going for. MS and MS will equal SQ, the whole thing. Okay, I know this through substitution. Okay, I know MS is equal to MQ. So I could plug the MQ in for the MQ, sorry, I could plug the MS in for the QM right there and substitute it out. Okay, and I can do similarly, I can take out the MP and I can take out the MR and I can also put those in MS's. All right, and so if SQ equals MS plus MS and PR equals MS plus MS, then I know for sure SQ must equal PR through substitution. SQ equals PR. So now I know for sure that this length, and I think we knew that before, but we just had to show it formally, and this length are actually congruent. So what I've actually done is proven that the quadrilateral is a rectangle. Okay, that's a good start. But to be a square, which is what we're going for, I actually need it to be a rhombus as well. So now I know for sure that these diagonals are congruent. I still know that every one of these little half bisectors are congruent. And I know that QRS is a parallelogram. Because if the diagonals of quadrilateral bisect each other, the quadrilateral is a parallelogram. Well, I already knew that. We knew that already because they did bisect each other once we proved that these were equal. But we didn't have it in our proof, so let's get it in there. And like I was saying, since we know that the diagonals just so also happen to be congruent, then we know for sure it's a rectangle. And like I said, you can abbreviate these if you need to. Once we prove that these were equal on both sides and these were equal on both sides, we knew it had to have been a parallelogram because they're bisecting. We knew it had to be a rectangle because not just are they bisecting, they're actually congruent diagonals. So prove a rectangle, you have to know that their diagonals are congruent. That's what we've done so far. And it continues. We know that it's a rhombus. We know it's a rhombus because we have diagonals that are perpendicular. Okay. We know that because in the given it said this is the perpendicular bisector, perpendicular bisector. So we knew for sure that these were perpendicular, the diagonals are perpendicular, the diagonals are congruent. So we knocked out rectangle because the diagonals were congruent. We knocked out rhombus because the diagonals are perpendicular. Therefore, PQRS must be a square because it is a rectangle and it is a rhombus. All right. So once again, I want to emphasize these long proofs come from when we have squares, because we actually have to do like a combo proof. We have to prove that it's a rectangle and have all those steps involved. We also have to prove that it's a rhombus, because a square is must have all the characteristics of a rectangle and a rhombus. Okay, and then once you know that, you're good, you're golden. So that's it for today. Some proofs. They're going to be fun. I'll see you on Monday.